In this video, we are going to find integers n such that n factorial is larger than the square root of n to the power n. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. Here is a table that lists out the values of n factorial and the square root of n to the power n when n takes some small integer values, say 1, 2, 3, up to 8. And you can see that starting from n equals 3, n factorial is always larger than the square root of n to the power n. So I'm just making a guess at this point that the answer to this, the solution to this inequality, is all positive integers n that's at least 3. So here's the claim, which is that n factorial is larger than square root of n to the power n for all n that is at least 3. And to prove this, the most apparent way is to prove it by induction. Now, of course, by comparing these values, we can see that the statement is true when n is 3, which is the base case. Now, assume that, say for some positive integer k, large enough, well at least 3, that k factorial is larger than the square root of k to the power k. Then let's see what happens for the case k plus 1. I can say that k plus 1 factorial is equal to k factorial multiplied by k plus 1. And by the induction hypothesis, this is larger than the square root of k to the power k, or multiplied by k plus 1, or k to the power k over 2 multiplied by k plus 1. And I want to show that this expression in blue is larger than the square root of k plus 1 all to the power k plus 1. We need to show this inequality. Then simplifying by first squaring both sides, we have k to the power k times k plus 1 all squared is larger than k plus 1 all to the power k plus 1. Then divide both sides by k plus 1 all squared, we have k plus 1 all to the power k minus 1 left at the right. Then to simplify things, I'm going to write the right side as k plus 1 all to the power k, all divided by k plus 1. So then all the powers in this inequality are k powers. Then I'm going to gather the k powers, combine them, so I have the inequality k plus 1 larger than k plus 1 over k all to the power k. Or I can simplify, or I should say rewrite the fraction inside the bracket as 1 plus 1 over k. So now the focus is, what values do these kind of expressions actually take? Recall that the limit of this when k grows to positive infinity is well known, and that's the exponential constant e. And we know that this e must be less than k plus 1 because this k is at least 3. And we know that e is about 2.71828, and so on. Now the final question is whether the expression in yellow, just a k power, is always smaller than the case when the k tends to infinity. So here's the final result that I need to prove before finishing this induction proof, which is, I'll call this a lemma, which is that the sequence is just the way to phrase things. This kind of sequence is monotonic increasing. Or, in mathematical language, I can just prove that 1 plus 1 over n all to the power n is always smaller than 1 plus 1 over n plus 1 all to the power n plus 1. If I can prove this, then actually I can just, it's kind of another kind of induction that tells us that 1 plus 1 over n all to the power n is always smaller than the case when, the limiting case when n goes to infinity. So let's try to prove this. In fact, I'm going to consider one plus 1 over n all to the power n over n plus 1. I'm going to rephrase this as the n plus 1 root of the product of the following n plus 1 terms. The first n terms are each 1 plus 1 over n, altogether n terms, multiplied by 1. Then, despite the AMGM inequality is less than or equal to the sum. And then all divided by n plus 1. So simplifying, for the numerator, we have altogether n plus 1 ones, so the sum is n plus 1, plus there are n terms of 1 over n, so n times 1 over n, all divided by n plus 1. And that's 1 plus 1 over n plus 1. So that means our inequality is now proven. Almost. It's just that we need to settle the equality case. But notice that these terms, the 1 plus 1 over n and the 1, are never equal, because equality never holds. That means this inequality is strict. So that means it's monotonically increasing. And so that means we're done with our proof. I can say that this kth power is always smaller than the limiting case, and that's always smaller than k plus 1. So the induction is true by induction on n. And that means we've concluded that our final answer is all positive integers n, that is at least 3. So this is the final answer. Please feel free to share ideas in the comments. Thank you for watching. See you next time.